All right, welcome to the Explainer. Ever stop to think about the app you just opened or the search you just made? Behind all of it, there's this invisible blueprint that makes it all work fast and feel effortless. Today, we're going to demystify that blueprint. Data structures and algorithms. Yeah, I know it sounds complex, but we're going to break it down.
So what is the secret sauce? What's the common thread that connects Google's massive search index, the GPS that gets you home, and the game that runs without a single stutter? Well, the answer is this incredible discipline for problem solving. It's all about turning these huge, messy problems into solutions that are just elegant and efficient. Okay, let's dive into this.
We're talking about data structures and algorithms, or DSA, as you'll hear it called. And at its core, DSA really just boils down to two simple ideas. First, how you organize your information, and second, the steps you take to actually use that information. Put them together, and you've got the fundamental framework for writing truly optimized code.
So let's start with data structures. At the end of the day, these are just specialized containers for your data. Think about it. If you had 1,000,000 books, you wouldn't just toss them in a giant pile, right? No way. You'd use shelves, you'd have categories, a whole system. Data structures are just like those shelves. They're the smart containers for information. They are basically the nouns of programming.
And then you've got algorithms. So if data structures are the nouns, well, algorithms are the verbs. They're the set of instructions, the recipe that acts on the data inside those structures to get you the result you want.
And here's the really crucial part. You can't have one without the other. They're a team. You could have the most perfectly organized warehouse in the world, that's your data structure, but if you don't have a forklift or a plan to move the boxes, that's your algorithm, then it's all useless. They absolutely have to work together to create efficient programs.
Okay, so that's all cool in theory, but why should you actually care about this? Well, it turns out DSA is critical for two huge reasons. One is about the actual code, and the other is about your career.
First off, DSA is what makes software feel fast and responsive instead of slow and clunky. It's the engine humming under the hood. But second, and this is a big one, if you want a career in tech, DSA is your key. It's how the top companies test your ability to think like a problem solver.
And look, this quote right here hits the nail on the head. We're not just talking about some academic exercise. Understanding these concepts is a direct line to getting a job at the biggest names in tech. They want to see how you think, and trust me, DSA is the language they use to find that out.
Okay, so let's say you've written some code. It works, but how do you know if it's any good? How can we actually measure if one solution is better than another one? This is where performance measurement comes in.
Because here's the thing, getting the right answer is only half the battle. The real challenge, especially when you're dealing with tons of data, is writing code that performs well, that's fast, and that doesn't eat up all your computer's resources.
We basically measure this in two main ways. First, there's time complexity, which is just a fancy way of asking, how fast is it? As my data grows, how much longer is this going to take? And then there's space complexity, which asks, how much memory does it need? And, there's often a trade-off. Sometimes the fastest code needs the most memory, and vice versa.
Now, to talk about all this stuff in a standard way, we need a common language. And that's where something called asymptotic notations comes in. I know, it sounds super intimidating, but all it really is a way for us to classify how an algorithm performs in different situations, like the best, average, and worst-case scenarios.
So this chart breaks it down pretty nicely. You'll hear about Big O all the time, and that's because it describes the absolute worst-case scenario. It's basically a guarantee that your code won't perform any worse than this. Then you've got Theta, which is kind of the realistic average case. And Omega is the best case, when all the stars align. But we usually plan for the worst, which is why Big O is so important.
So now that we have a way to measure performance, let's actually open up the toolkit and look at some of the most fundamental data structures you're going to see everywhere.
First up is the array. Seriously, this is the absolute workhorse. It's just a simple block of data where every element is stored right next to each other in memory, kind of like a row of numbered parking spots. And that structure is exactly what makes it so incredibly fast to jump to any specific element. And then we have the linked list. Now, this is totally different. Its elements can be scattered all over the place in memory. It's much more like a scavenger hunt, where each item doesn't just hold data, it also holds a pointer that tells you exactly where to find the next item in the chain.
So what's the trade-off here? Well, it really boils down to structure versus flexibility. Arrays are rigid, they have a fixed size, but you get that lightning-fast access in return. Linked lists are super dynamic. They can grow and shrink easily. But if you want to get to an item in the middle, well, you have to follow that chain all the way from the beginning.
Okay, next up is a stack. This one is super easy to picture. It follows one simple rule: last in, first out, or LIFO. It works exactly like a stack of plates. The last plate you put on top is the very first one you grab when it's time to eat. The undo button in your text editor, that's a stack.
A queue is the complete opposite. It follows the first in, first out principle, or FIFO. And this is just like a line at a coffee shop. The first person to get in that line is the first person who gets their coffee. Simple as that.
So the crucial point here is that this one simple difference in the order of operations changes everything about what they're good for. Stacks, LIFO, are perfect for things that need reversing, like that undo button. Queues, FIFO, are ideal for processing tasks in the exact order they arrived, like jobs sent to a printer. And finally, we get to the really interesting non-linear structures. You have trees, which are all about hierarchy, just like a family tree or the file folders on your computer. And then you have graphs, which are these amazing flexible networks of connected points, kind of like a map of all your friends on social media, or even a map of the internet itself.
So after seeing all of these, you start to realize something pretty important. Every single one of these data structures is a specialized tool. There's no single best one. There's only the best one for the specific job you're trying to do.
And that right there is the real art of programming. Mastering DSA isn't about memorizing a bunch of definitions. It's about understanding the trade-offs of each tool in your toolkit so that you can look at a problem and know with confidence exactly which structure and which algorithm is going to solve it in the most efficient way possible.
So there you have it, a whirlwind tour of the fundamentals of data structures and algorithms. We have really only scratched the surface of this massive, fascinating world. But now you've seen the toolkit, you understand the basic principles, so the only question left is, what problem are you going to solve first?